arithmetic ciphers that we've seen. We looked at Caesar and Vigenère and AutoKey. You're always adding the same thing. So for Caesar, you always add 3 to every letter in the message. And for Vigenère, you always add a keyword. And for AutoKey, you add the keyword and then the message itself. So the encoding process was always addition. So it might be natural to ask the question, what about multiplication? Can we use multiplication as our encoding device? So that's what we call an affine cipher. If you multiply by a constant number and then add a possibly different number. So if you combine multiplication and addition, we call it an affine cipher. Strictly multiplication, we call it a multiplicative cipher. So for example, I'm going to encode the message attack at daybreak using an affine cipher where you multiply by 3 and then add 5. So I take each letter in my message, convert it to a letter, the equivalent number in the alphabet. Put in some vertical lines here. Okay, so my encoding process says multiply by 3 and then add 5. So no keyword or anything, just take each number, multiply it by 3 and then add 5. Okay, so I'll just do the times 3 part first. So 0 times 3 is 0. 19 times 3, might need a calculator here. 57. 57. 0, 2 times 3 is 6, 10 times 3 is 30, 19 times 3 is 57, 3 times 3 is 9, 24 times 3, 72, 17 times 3 would be 51, 12, 0, 30. Okay, so I multiply them all by 3. Now I add 5. So I take each of these numbers that have been multiplied by 3 and add 5. So I get 5, 62, 5, 11, 35, 5, 62. 9 plus 5 is 14, 77, 8, 56, 17, 5, 35. Now, convert them back to letters. However, some of them are too big, right? So what do you do when they're too big? Subtract or add 26, whichever will help. So in this case, I would subtract. Yeah, you're going to have to subtract it more than once. Yeah, because 62 minus 26 will still be too big. So we'll just repeatedly subtract. Or you can divide by 26 and give the remainder, because repeated subtraction is division. That's how division is defined, as repeated subtraction. Okay, so 5 is fine. It's already between 0 and 25. 62, I could do 2 different ways. I could start with 62 and subtract 26 until I get a number between 0 and 25. So I get 10. Okay. Or you can do 62 divided by 26. 62 divided by 26. And your calculator is going to give you a decimal as opposed to the remainder. I want to know the remainder. Calculator can't tell you that. So all my calculator tells me is that 26 goes into 62 2 times, 2 whole times, and there's some left over. To figure out how much is left over, I'm going to say, well, 2 times 26, like going backwards, because I know 26 goes in twice, so 2 26s is 52, and 62 minus 52 is 10. That's my remainder is 10. So you can use your calculator to figure out remainders, but it can't just tell you the remainder. Okay, so that's an important thing. A lot of people just look at this decimal and want to know how do I get the remainder. you have to say 26 goes in 2 whole times. So 2 26s is 52, which means there's 10 left over. 52 from 62. Or just repeatedly subtract the 26. You're not going to have to do it that many times, so you could just do the subtraction. Okay, so that one's also 10. 5 is fine. 11 is fine. 35 is too big. When I subtract 26, I get 9. 5, 62 becomes 10. 14, 5, 77 is too big, so I'll do 77 minus 26. Too big, minus 26. 25. Okay, good. 8 is fine. 56 is too big. Minus 26 would give me 30. Minus 26 is 4. 17, 5. 35 minus 26 is 9. Then change them all back into letters. So, thank you. There we go. So now we have encoded it by using multiplication and addition. Makes the code that much harder to break if you're applying 2 steps, 2 different encoding. So we've basically encoded it twice using 2 different codes, a ×3 and a +5. All right, so we know how to encode the message using an affine cipher. How do we decode? Okay, so we have to undo what we did. So we first multiplied by 3 and then added 5. So to undo, we should start by subtracting 5. But then how do you undo multiplication by 3? Yeah, that would be our natural answer, right? To divide by 3. So that's usually how we undo multiplication by 3, but it's not really possible in modular arithmetic, right? Because you can only have answers from 0 to 25. And if I have something like, let's take a look at my results here. If I'm trying to go backwards, let's say I take 10, I subtract 5, I get 5. 5 divided by 3 isn't a whole number, right? And I need a whole number from 0 to 25 because those are what corresponds to letters. So it doesn't actually work in modular arithmetic to divide by 3. So this is my encoding process. So when I start to encode, I start with a t, which is a 19. I multiply by 3, right? And 19 times 3 is 57, which is equivalent to 5. And then when you add 5, you get 10. Okay, so t goes to f and then goes to k. So when I go backwards, I need to start with my 10, subtract 5, and I get 5. And then I need to do something to get my 5 back into a 19. Or something equivalent to a 19. So it turns out there is a way to undo multiply by 3. And it turns out to undo multiplication by 3, you multiply by 9. What? Right? Yeah, you undo multiplication by 3 by using multiplication again. And let's think about why. Think about why. So if I multiply by 3 times 3 and then times 9, so I've got some number. To encode it, I multiply by 3. To decode, multiply by 9. What's 3 times 9? 27. What number is 27 equivalent to in mod 26 arithmetic? B, which is the number 1. So that's my number times 1, which gives me my number back. So multiplying a number by 3 and then by 9 is the same as multiplying a number by 1, which gives you the number back. It's kind of crazy. Do over? Okay. Okay. Let's pick a letter. Let's pick T. Okay. So T. To encode it, it's a 19. Right. Then I'm going to multiply by 19 by 3 and you get 57. And then I'm going to add 5 and I get 62. Take that mod 26. So 62 minus 26 minus 26 is 10. Whoops. It's 10, yeah. It's 10. Okay, and then 10 gets encoded as the letter K. Okay. So to go backwards, I'm going to work my way backwards here. So start with a K. Encode it as a letter, it's a 10, right? To undo, I should undo in the reverse process that I did, right? So the last thing I did was, right, but ignore the modularizing part. We always save that for the end. Okay. So to encode, I multiplied by 3, then added 5. So I'm going to start by subtracting 5. 10 minus 5 is 5. And then instead of dividing by 3, which would be your normal way of undoing multiplication by 3, I'm not going to do that because 5 divided by 3 doesn't give me a whole number. And I can only work with whole numbers because only whole numbers correspond to the letters. So instead of dividing by 3, I'm going to multiply by 9. 5 times 9 is 45.
So where does the 9?
I'm giving it to you for now. Yeah. Telling you for now. That's how you undo multiplication by 3. So I changed to a letter. Subtracted 5. And then times 9. So the times 9 is supposed to be the thing that undoes times 3. So you just have to take my word for it for now. But then 45 is too big, right? So subtract 26. 19. And 19 corresponds to T. So it does get me back to where I want to be. If I start with T and encode by doing times 3 plus 5, I decode by doing minus 5 times 9, gets me back to my T.
So is it always this style of
The affine cipher? Yeah.
Nope.
Nope.
It was times 7.
It's such a good question. It would be you would undo times 7 with a different number than you would undo times 3. So it wouldn't be times 9, it would be times something else. Yeah, you can. So I'm saying, okay, I have some number. To encode it, I'm multiplying by 3, right? In this example, I'm multiplying by 3. I'm saying, okay, what do I need to multiply by so that I end up with this number times 1? Or something equivalent to 1. Which would be like 27 or 54. Is 9 equivalent to 1 in mod 26 arithmetic? So I need this to be 1. So 3 times 12 is 36, right? Is 36 equivalent to 1 in modular arithmetic? So what's 1? B is 1. Yep.
Exactly, B is 1, so it has to be
Yes. So a number that when you subtract 26, you get 1.
so
What number would that be?
3 by
27. Yeah. So 1. So I need 3 times something to give me 1, right? But there is no number from 0 to 25 that you can multiply 3 by to get a 1. So, but a number that's equivalent to 1 would be 27, right? So what should I multiply 3 by to make it 27? 9. So 9 is what you multiply by to undo multiplication by 3. Because multiplying by 3 and then by 9 is the same as multiplying by 1. Let me bring it back to our standard arithmetic so you can see what the analogy. Okay. So if like you guys all said before, multiplying by 3, you normally undo that by dividing by 3, right? Or multiplying by a third, right? So if I have something and I want to multiply by 3 and I need to multiply by something to undo that, I'm saying, okay, well, 3 times what? I need this thing to be 1. So in standard arithmetic, this thing would be a 1/3, right? I would say, oh, well, 3 times a third is 1. So the way you undo multiplication by 3 is multiplying by a third, because then I've really multiplied by 1. But in modular arithmetic, a third isn't a number. We only deal with whole numbers in modular arithmetic. So I have to come up with a whole number that I can multiply 3 by to make 1. And the only way to do it is to have other numbers that are equivalent to 1, bigger numbers. Yeah.
That does work. We're looking at it. When I'm trying to like resolve that, I mean, on paper, maybe if we're like, if we stop to take 1/3 and compare that to like the 26 letters, we're not gonna find it. But if we know that that works, anyways, can't we still do that? And
Let's see what happens. Let's say I start with t, right? Which I change to the number 19, which gets multiplied by 3 and I get 57. Add 5, I get 62. Modularize, I get 10, and that gives me k, right? So to undo, so this is do, undo, start with k. First thing I want to do is subtract 5, or change it to a letter. It's 10, right? Subtract 5, I get 5. And then you're saying times a third works, right? To undo times 3, you multiply by a third. But if I multiply 5 times a third, I get 5/3, or 1 2/3. And what the heck does that mean? What letter does that correspond to? Yeah. So then, now what? So I can't do times a third.
I understand 26. I understand 27.
Okay. Yeah, okay, good. So, okay, let's look at another example. So I'm looking for a way to undo multiplication times 3, right? So I need to multiply by something else so that multiplying by 3 and that thing is really multiplying by 1. So in standard arithmetic, multiplying by 3 followed by a 1/3 is the same as multiplying by 1, so nothing changes. I would get my number back. If you have some number and you multiply by 3 and then you multiply a third, you get your number back. Okay. So in modular arithmetic, if I have t, right? t becomes 19, times 3 is 57, plus 5 is 62, modularize, I get 10, that becomes a k. So to undo, k gets converted to a 10. Subtract 5, I get 5. And now to undo the times 3 part, I need to I can't multiply by a third, it doesn't work, right? So I have to come up with something that I multiply by that will give me my original number back. Okay, so I've already multiplied my number times 3. So I'm looking for, I took my 19 and I multiplied it by 3 to encode. So to decode, I need to multiply by something else, right? So this is encode. This is my decode. So I want to do 19 times 3 times something else that will give me the 19 back. With me so far? So when I encoded, I started with my 19, I multiplied by 3. Now I have to find something else to multiply by, so I'll get my 19 back. Okay. So my encoding and decoding, when I multiply times 3 times my decoding factor, those two things together have to be like multiplying by 1 in order to get the 19 back. Because 19 times 1 will give me 19. So I have to have 3 times something equals 1. But there is no number between 0 and 25, whole number between 0 and 25 that I can multiply 3 by to make a 1. No, because 3 times 1 is 3.
Oh, 1.
Yeah. So instead of 1, say I'm looking at this and I'm going, there is no such number. I can't use a third because I can only use whole numbers. There is no number that I can multiply 3 by to make a 1, unless I'm allowed to use fractions, and I'm not. So instead of 1, use a number that's equivalent to 1 in mod 26. 1 and 27 are the same in mod 26. They're both b, right? So then I say, well, there is a number I can multiply 3 by to make 27. And 27 is equivalent to 1, so I'm going to use that. Use 9.
What if 7?
Okay, we'll get there. We'll get there.
Then you just use a bigger, you use a 1 plus a larger multiple of 26. Like,
So I'm going to multiply my 5 by my 9, and I get a 45. So this is minus 5 times 9. 45, when you modularize, subtract 26, you get 19, which is t. So this was times 3 plus 5. All right, so good question. What if the encoding key is 7? We multiply by 7 and not 3. So I would say, okay, I've got some number. I'm going to multiply it by 7 to encode, right? And then I'm going to multiply by something that I don't know to decode, and I need to get my original number back. So I need this. I need 7 times this unknown decoding factor to be 1, or something equivalent to 1, which could be 27. But you say, is there a number I can multiply 7 by to make 27? No. So pick another number that's equivalent to 1. Add 26 again. So 1 is equivalent to 27 because you can always add 26 and you'll land back at the same letter, right? So 1 plus 26 gives me the 27. Add 26 again, and I get 53. Is there a number you can multiply 7 by to make 53? No. Okay, so add 26 again. 79. Does 7 go into 79? Nope. Plus 26. 105? I don't think so. Oh, it does? Okay. 105 divided by 7. Yeah, it goes in 15 times. So that ended up being 105 was our one that worked. So 7 times 15. So that means this is my number times 105. 7 times 15 is 105. But 105 is equivalent to 1. So I got my number back. So if you multiplied by 7 to encode, you have to multiply by 15 to decode
You just keep going higher.
until you find one.
That works.
Yep.
Maybe like 1,000.
It could be really high, yeah. All right, so with modular multiplication, you undo multiplying by 3 by multiplying by 9. All right. How does that work? Because when you multiply by 3 and then by 9, that's equivalent to multiplying by 1. So it's like you haven't changed anything. You get your original number back. So 3 and 9 are called multiplicative inverses in Mod 26. Or inverse operations. They undo each other. If you multiply by 3 and then you multiply by 9, they undo each other, so we call them inverses. Finding these inverse operations is the key to using multiplication to encode and decode. You have to be able to figure out the multiplicative inverse, which, as we just saw, can be difficult. Can be time consuming. If you have to use a really high multiple of 26 plus 1, it can take a while to find it. That makes breaking the code take longer, which is always a good thing. So the question is, can any multiplication operation be reversed? What if we multiplied by 6? So you chose 7, which was a good one because it worked. We were able to find an inverse. But if you multiply by 6, notice that A becomes 0, 1 becomes 6, so B goes to G, but then O also goes to G. Right? So when I'm decoding, if I have a 6, should it go back to B or back to O? It's impossible to know where we started. So 6, multiplying by 6 is not reversible. You can't use that as your encoding key. So if we wanted to decode a message that has a G in it, there would be no way of knowing if it started as a B or an O. Can't use this operation. It's not reversible. The problem is even worse if you try to multiply by 13. Every number becomes either an A or an N. Right? Every number gets encoded as A or N if you multiply by 13. So it's totally impossible to encode a message to decode a message that was encoded this way. All A's and N's, how the heck do you undo that? 6 and 13 are not reversible. So how do we know in advance whether a particular multiplication operation will be reversible? So it turns out that if we multiply by a number that shares a common factor with the modulus, the operation will not be reversible. So 13 shares a common factor with 26 because 13 goes into both 13 and 26. 6 doesn't work because 2 is a factor of 6 and 2 is a factor of 26. They share a factor. Yeah, so any even number won't work as an encoding key if you're using mod 26. 3 and 26. 3 is the first one we did. That one worked because 3 and 26 have no common factors. There's no number that divides both 3 and 26. So for this reason, because there are so many encoding factors that you can't use with 26, often we change the modulus from 26 to a prime number, because then it's highly unlikely that they'll share any factors. So a prime number, remember, only has divisors 1 in itself. So like 3, 5, 7, 11, 13, those are all primes. So 27 is not prime because 3 goes into 27, 9 goes into 27. But 29 is prime, and it's pretty close to 26. So often when we use this kind of encoding, we'll use mod 29 instead of mod 26. Yeah, that's a good, you could do that because we would have 3 extra symbols, 26 letters, and then there's 3 extra symbols. You could assign them like punctuation, or we could just not change things back to letters and leave our message encoded as a string of numbers. Whichever one. In general, the way it is typically done is to just leave the message encoded as numbers instead of doing that last step and turning it back to letters.
Well, if you're trying to decode that, you end up, well, I guess you just know that anything over 26 is not a letter.
Right. When you're decoding, you'll actually never end up with something over 26
Okay.
because what you started with never started with something over 26. So when you encode, you might get something bigger than 26, but when you decode, it'll always take you back to what you started with. So the advantage of using a prime number modulus is that you no longer have to worry about the numbers you multiply by sharing a common factor with the modulus. So the disadvantage is that our modulus is now bigger than 26. So let's go ahead and encode one. Retreat it once. We're going to use multiplication by 6. That's how we're going to encode, multiply by 6. And we're going to take the result mod 29 instead of mod 26. Okay, so that means subtract 29 over and over again. This is called mod 29. Yeah. All right, so my encoding is multiplication by 6. Put in some lines here. Okay, so 17 times 6. Okay, thank you. 4 times 6 is 24. 19 times 6. 14. I have another 102. 4 times 6 is 24. 0 times 6 is 0. 19 times 6 is 114. 0. 114. 14 times 6. 13 times 6 would be 78. 2 times 6 is 12. And 4 times 6 is 24. Okay, so encoded by multiplying by 6. Now, usually we would, anytime we have a number that's too big, we would subtract 26. But instead, we're going to use 29. Okay, we're changing our modulus to 29. So now we subtract 29 until you get a number that's appropriately sized. So take our 102, subtract 29 over and over again. 102 minus 29 minus 29. You could also divide and give the remainder instead of repeatedly subtracting. 15. Okay. 24 is already small enough. 114, too big, so I'm going to subtract 29 over and over again. 27. Now, normally, I would say, well, that doesn't correspond to a letter. It's too big. But my mod is 29, right? So if I were to subtract 29 again, I'd get a negative, which also doesn't correspond to a letter. So I'm just going to stop here at 27. This is the disadvantage of using mod 29, is that sometimes when you encode, you're going to get numbers that correspond to no letter. The way we solve it is we just say this is the encoded message, a list of numbers instead of a list of letters. Nope. $84, subtract 29. $26. And then 78, subtract 29, 20. And then I have 12 and 24. Okay. Now, the last step is usually to change each of these into letters, but I have a bunch of 27s in there. which corresponds to no letter. So I could either, like you suggested, assign 26, 27, and 28 to be some sort of punctuation, like, or other symbol, or I can just leave this as a list of numbers. Just say, this is the encoded message. I'm going to email this list of numbers, and someone will just decode it from there. So here it is encoded. We get results like 26 and 27. Can't change them back into letters. So when we use multiplicative or affine ciphers, if you use a mod greater than 26, we simply leave our encoded message as a sequence of numbers instead of changing it to letters.
So why another one for the options?
Because when we had mod 26, 25 was the very last number because we were using mod 26. There were exactly 26 letters. So when I got to 25, I could wrap back around, right? But maybe I can write it out. So okay. So 26, when we're dealing with mod 26 arithmetic, 26 would wrap around to A and be 0. Okay. 27 we'd wrap around, that would be B, which is 1. But when we're dealing with mod 29, you can't wrap around here, right? Because there's more there's more spaces here. We have 26, 27, 28. We have like 3 blanks. So 26 just doesn't correspond to anything. And when I get to 29, then I can wrap around. That's what mod 29 means. It means you don't wrap around until you get to 28. So I could assign, symbols here. I could make this be an exclamation point. I could make this be an asterisk and a dash if I really wanted to be able to convert this into letters at the end. But why bother? Just leave it as numbers.
So it still decodes normally.
It does. Yep. So let's say we want to decode a message that was encoded using a multiplication by 6 and the result taken mod 29, like the example we just did. We need the multiplicative inverse of 6 in mod 29 arithmetic. Okay, so I need, to get the multiplicative inverse of 6, I need to know 6 times what gives me 1 back in mod 29. Okay, so I asked myself first, is there a number you can multiply 6 by to get 1, a whole number? Yes, 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 perfect, yeah. If I'm just thinking about 1, no, there isn't one. So I come up with an equivalent number to 1, which in mod 29 arithmetic is 30. 30 is equivalent to 1 in mod 29 arithmetic, because go back to this, right? Mod 29 arithmetic, you get to 28, 29 wraps it back around. 30 is equivalent to 1.
So wait, this is mod 29 right here, and A is 0?
Yeah.
Is A is 0 in mod 26?
Yes, A is always 0. So in mod 29, any number that has remainder 0 is equivalent to 0. Any number that has remainder 1 is equivalent to 1 when you divide by 29.
So if you're encoding, you encoded it multiplication and no addition, and your A's are like 5 vowels.
Yeah. Yep. Yep. Yeah, good point. So 30 in mod 29 arithmetic is equivalent to 1. Because take your 30, divide by 29, remainder is 1, right? So 30 and 1 are the same. So then you say, is there a number you can multiply 6 by to make a 30? Yeah, it would be 5. So if you encode using 6, you should decode using 5. So you say 6 times what is 1? Well, nothing, so come up with numbers that are equivalent to 1, in this case 30, and that number would have to be 5. So we say 5 is the multiplicative inverse of 6 if we're in mod 29 arithmetic. So I want to use that multiplicative inverse that we just found, the 5, to decode this message. So this message was encoded by multiplying by 6, taking the result mod 29. So to decode, I should multiply by 5. 5 is what undoes multiplication by 6 in mod 29. So I'm going to take each of these and multiply by 5. 15 times 5 is 75. 24 times 5, 120. 135, I think. Yep, 75, 120. 0 times 5 is 0. 135, 0. 26 times 5 would be 130. 20 times 5 is 100. 12 times 5 is 60. 24 times 5 is 120. So now these numbers are all too big. So I'm going to take the mod 29, subtract 29 over and over, or divide by 29 and give the remainder. Okay, so 75 minus 29, too big, minus 29 again, 17. 120, mod 29, 10, 135, 25, 19, okay. Really? Are you sure? Seems like it should be 15 bigger than 10. Maybe not. Okay. All right. So 75, so we get 17. 10, 0 is already small enough. 135 is a 19. 0, 19. 130. 14. 100. 60. And 120 we already know is 10. So then we change these to letters. 10 is K. What's okay, we screwed up there's something wrong with the beginning. Let's see. 75 divided by 29. Oops. Goes in twice. 2 times 29 is 58. Remainder is 17. And that's an R. That's right. Okay, so then 120 divided by 29. 4 times 29 is 116. So that's a 4. And then That's an E. 135 divided by 29, so 4 times 29. 135 minus 116 is 19. And 19 is a T. And 75, 17, that's an R. And 120 goes to 4, that's an E. So our message is retreat at once.
Too late.
It took too long to decode. Oh, I had it all. What do you need? This? Yeah. So that was good to review because we're going to do another one.
What was the undo part?
Times 5. When we decoded just now, I did times 5. Because to encode, I multiplied by 6. So to decode, I multiplied by 5. Because right before that, we figured out that that's how you decode. No, 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 no. Say that again. No, I didn't have the 5 yet. I got the 30 before the 5. The 30 is how I figured out the 5. Okay. So I was saying 6 times what will give me 1, right? And I was like, nothing. There is nothing. So then I converted the 1 to a 30 because they are the same in mod 29 arithmetic. You can always add 29. You can always add the modulus and you'll land at the same place. So 1 plus 29 is 30, and then I could figure out, oh, 5 is what you multiply 6 by. So the 30 didn't come from the 5. The 5 came from the 30. That makes sense. Okay, so here's another one. What if we encoded by multiplying by 7? If your encoding factor is times 7, and we're using mod 29 arithmetic, I want to know how should I decode. So to find the multiplicative inverse, I say, okay, well, 7 times what? Oops, times, not plus. 7 times what will give me 1? So there is no whole number that I can multiply 7 by and get to get 1. So give me a number that's equivalent to 1 in mod 29 arithmetic. Nope, that was mod 26. We were working in mod 26 when we did that one. 30, yeah, still 30. You can always add 29. You can always add the modulus and get an equivalent number. So 30 is equivalent to 1. So 7 times what gives you 30? There isn't one, so we need to come up with another number equivalent to 1. How do I get another number equivalent to 1? Add 29 again. 30 plus 29 is 59. Is there a number you can multiply 7 by to make 59? Nope, so do it again. 7 times what gives you 59 plus 29 would be 88? The 7, 175? Okay. Okay, so 7 times 25 gives 175. And 175 is equivalent to 1. So 25 is the number you decode. You use decode by multiplying by 25.
So the first step is always going to be 29 plus whatever the mod is plus 1.
Mm-hmm.
And you're just adding the mod after that. You're not adding.
Right, just adding the modulus. Yep. Well, and you can think of the first time as the same thing because we're looking for 1, right? Plus 29, plus 29, plus 29. Yeah. So 25 is going to be your multiplicative inverse of 7. All right, so We know using prime numbers means it will always have a reversible multiplicative cipher, but in general, finding the inverse operation can be difficult, right? We didn't even write them all out. Between 88 and 175, you have to add 29 several more times, right? So this can take a long time to find. And the bigger your modulus, the longer this can take to find, right? 29 is not so large. You know, we can just keep adding 29 and we will find it eventually. Okay, but when you have large prime numbers, it gets even more difficult. This is an example of an asymmetric cipher. That means that the method for decoding is not easily determined even if you know how we encoded. So even if you knew that your encoding key was times 7, finding that decoding key of times 25 is at least time consuming. Not impossible, but time consuming. So these are called asymmetric ciphers, where it's difficult to figure out how to decode even if you know exactly how it was encoded. Asymmetric ciphers are what allow for public key cryptography. So in a public key system, everyone has 2 keys, a method for encoding messages and a method for decoding messages. With a multiplicative cipher, these keys are numbers. The encoding key is the number you multiply by to encode, and the decoding key is the number you multiply by to decode. So the difference in a public key system is that the encoding keys are made public. I would just post out on the internet. I would just say, hello everyone, if you want to send me a message, encode it by using multiplying times 7, and then send it to me. And then only I am smart enough to figure out how to decode it, because only I know modular arithmetic, right? Only I could figure out that to decode multiplying by 7, you should multiply by 25. Does this make sense? That's not really the case, right? But if you use a really, really, really big prime number, like if I say instead of multiply by 7, multiply by the largest prime number you can think of that's like 100 digits long, then only I could know the decoding key, and no one else could figure it. It would take too long for someone else to figure it out. Technically, you can figure it out by doing what we just did, but it would take so long that even a super powerful computer would take years to do it, and by that time, the info in your message is irrelevant. So everyone knows everyone else's encoding key. Everyone posts in some public space how to send them an encoded message. And then you have your own private decoding key that only you know. And it's too difficult to figure out the decoding key from the encoding key in a timely manner. So this is sort of how it works. So suppose Adam wants to send a message to Beth. He encodes his message using Beth's public key. Okay? Only Beth knows her private decoding key, so only Beth can decode the message. But anyone can send a private message like this to Beth. Anyone can look up the encoding key for Beth, write a message, encode it using that key, and send it to her. But only she knows how to decode it. So think about it this way. Using Beth's public key to encode a message is like putting in a special kind of box. It's like putting your message in a special kind of box that only Beth can open. So let's say that Beth's boxes are blue. Only Beth can open blue boxes. Anyone can go to the store and buy blue boxes and put something in and send it to Beth, but only Beth can open blue boxes. Just because you know that the message is blue doesn't help you open it. And let's say Adam's boxes are red. Anyone can go to the store and buy red boxes so that they can send Adam a message, but only Adam can open red boxes. So if Christine sends Adam a message encoded using his public key, she doesn't have to worry about Beth intercepting the message because Beth can't open red boxes. Okay. So affine and multiplicative ciphers are substitution ciphers, which means that they're susceptible to techniques like frequency analysis. So these are unsuitable for public key cryptography. Because in public key cryptography, you really need the codes to be virtually unbreakable. Not just that it would take you 20 minutes to figure out the decoding key, but it needs to take you years. So the most common system in use today is RSA cryptography. It relies on the same ideas we've talked about, modular arithmetic, large prime numbers. But the prime numbers we use for RSA are so big. Like when you see, you'll see like 64-bit encryption. You see like sometimes when you go to a secure site, it'll tell you that. I believe that that means that the prime number you're using has 64 digits in it. So it's a super, super long prime number whose decoding key would be take way too long to find. Mm-hmm. Yep. Yeah, so for example, here's a typical security message. It says 128-bit encryption. So that means, it means that the encryption key could be as large as 2 to the 128, which is a 39-digit number. So even if a computer could check manually for a decoding key, if they could check 1 billion keys per second, it would still take 10,000 billion years to check them all. So that makes it virtually unbreakable. Far, far longer than the age of the universe. So RSA relies on the size of the key being large enough to make breaking the code take an impossibly long amount of time.
So the size of key is the only requirement.
Yes. Yep. Very large prime number. Prime number is the key. So that's just a little taste of public key cryptography, how it works on the internet. We just did a baby example with modular arithmetic, so you could get the idea of using prime numbers and it taking longer and longer to find the decoding key. So your homework, again, is the worksheet. That's right after class 26. And you've got 7 or 8 minutes that you can start it now.